Hello everyone, I'm Sanket and I work with LinkedIn as an SRE. And today we are going to talk about how we use machine learning to detect application hotspots. So let's get started. Here's what we'll be talking about today. We'll take a look at the LinkedIn site and how we perform load tests in that. We'll take a look at the opportunity that we have when we perform this load tests. And finally, we'll see what is the approach that we use to detect this application hotspots. We'll see how we used to do it earlier, and we'll see how we're doing it now. And finally, we'll see the results, as in how the approach is performing. What we won't be talking about today is the math part of the approach. So you do not need to be a machine learning expert to make sense of this talk. So let's get started with the LinkedIn site and the load test. At LinkedIn, load tests are a daily practice. And what we do is we reroute member traffic to a target data center. So if you look at the overall traffic graph of the target data center, here's what it will look like. And if you see in the red box, that is the window it is being load tested. If you want to read more about load testing and how we do it, that's the blog that my colleague has written. How it happens is all the requests that comes to LinkedIn goes through one of the edge hosts. And what edge hosts have is a service called sticky routing service. So what this service is capable of doing is reroute the request to any of the LinkedIn's data center. Let's say we are load testing data center one. So what will sticky routing service will be doing is send a lot of traffic to that data center and in result load test data center. There are certain challenges when you do this. The first being the forecast, how much traffic should we be sending to the data center. My colleague in last SREcon gave a talk on the forecast part of this load testing if you want to know more about it. And the other challenge is it is a real member traffic. So that means if there is any outage, actual LinkedIn users will be affected. However, there's an opportunity as well. We get to see services behavior under stress, and this is real member traffic. So instead of generating synthetic load, which will not be very much closer to the real traffic, we get to see this under real traffic. And because the service is under stress, we can run these calculations and identify anomalous services, the so-called hotspots. So to recap, LinkedIn runs out of multiple data centers. Edge hosts drive traffic to those data centers. We concentrate traffic to one data centers using this architecture. And when we do this, we analyze services under stress. So let's seize the opportunity. Before we go further, let's revisit some topics. So the LinkedIn service is it's a stateless microservices. So we have thousands of microservices based Java-based services, which is made on RESTly framework, which is open source by LinkedIn. And what is the unit of hotspot that we're detecting? Is it a host? Is it a service? Is it an endpoint? Is it a combination? So in this context, a hotspot is basically a service and its endpoint. So our thousands of microservices each will have some endpoints, and what we'll be detecting as a hotspot is a particular endpoint of a particular service. So the task at hand, we want to capture service situations that don't immediately cause outages, but they potentially could in future. So when we perform this load test, of course, there are actual alerts set up, and if any service is regressing, the on-call will get paged and they'll know. But what we are more interested in is the services that didn't trigger any alerts, but they could if we increase more traffic to during a load test. And to identify these services, what we use as signals is latency and error. So in our experience, any of these degradations or most of its degradations will be caught by one of these two signals. Here's how we used to do it earlier before the machine learning approach came in. So what we used to use is basically the mathematical formulas. So we tried mean plus x number of standard deviation. We also tried interquartile range, so there is 25th and 75th percentile middle point, and the error from the mean. And we did a lot of tuning as well. So if service is having low traffic, that means standard deviation is expected to be more. If service is having more traffic, then the deviation will be less. So what I mean to say is we did a lot of tuning based on these approaches. What we also did later is add GC and threshold metrics, but unfortunately it did not increase a lot of quality. The reason being If any of these went wrong, like if there's a high throughput utilization or if there's a GC issue, it will end up in increased latency or increased error count. So that is the reason why we did not see an increase in the results. What we also tried later is a page rank sort of algorithm. So as I said, it's thousands of microservices and all services calling each other. So what we did is if service is getting called by a lot of services, we rank it higher because that is an important service. So we tried that as well. As we did more investment in this approach, we are tuning a lot of parameters. At some point, we started hitting a plateau. So the investment in the approach was not resulting into better detection. So at that point, we started exploring machine learning. And at this point, we started a partnership with machine learning team at LinkedIn, so basically data science org. And the premise behind using machine learning was that we can make this baseline metrics calculation better. Uh, if we revisit the background, so how services behave is there's a traffic that comes to LinkedIn data center and services react to it. So basically, there is site traffic and there is the signal. So more site traffic would mean that more signal. So as the LinkedIn data center receive more traffic, latency will increase or error count will increase. And if you look at this relationship, it basically is a linear regression. So there is a relationship between the site traffic and the signal. So this is the basis of the approach, the model that we'll be creating. And how we create this model is using Python and Celery framework. So what we do is we train these models daily, and we use 15 days of data as the training data. And why 15 days is because we want to ensure that latest changes in service behavior are accounted. So let's say a commit was made, say a few days before, and that commit results into more latency. So we want to make sure that these models have this behavior accounted in them. And once these models are trained, we store it in MySQL. And whenever they are needed, we just query it out of MySQL. So now we have the models trained, pre-trained daily. So let the detection begin. Detection is a 5-step process. What happens is we have a daemon which monitors traffic of each data center. As soon as the daemon detects that there was a load test, the traffic went high. And as soon as it comes down, so that means the load test has finished, it triggers the detection. Next, what happens is the models are loaded from the database, those pre-trained models, and will fetch the actual metrics, like how much was the latency, actual latency during the load test, what was the error during the load test. So we'll load these actual metrics. We'll run some calculations, which we'll be talking about. What are those calculations? And once calculations are finished, we notify the service owners if their service is detected as a hotspot. So we'll send email, we'll send Slack to let the owners know that, hey, your service is detected as a hotspot and you might want to go ahead and look into it. So coming to the calculation, there are multiple things that we do. So we have some severity scoring techniques. So it will tell us how severe is the service. And we have some filtering techniques. So that will be filtering out a lot of the services. And the first technique that we started off with is called latency severity score, LSS. So what happens in this technique is we calculate the severity. So we have that model. We'll feed in the data center traffic, and it'll tell us that this service, this endpoint is supposed to be having this much milliseconds of latency. And if the actual latency is higher than that, that means it is out of bound, and we calculate a severity score for that. Since we have thousands of microservices, this will produce a lot of services, and we'll be needing some filtering techniques later on. And on top of that, again, we did the page rank algorithm on this as well. So what this means is if a service is important, is getting called by a lot of other services, that service's severity score will be ranked bumped higher. So page rank, basically, we rate by criticality of the service. After that, we do something called call path grouping. So as I said, like there are thousands of microservices and each service is calling other service. And what happens in this case is if we have a chain of hotspots, one of them is a bottleneck and the rest of the services are basically an effect of that. So let's say we have service A, B, C, A calls B, B calls C. So what we noticed is in any of these three cases, service is likely to be a bottleneck. So let's say if a service is a leaf node, so A, B, C, and there's no hotspot below C, C can be hotspot. Or if a service is having the highest severity score, so let's say B is having highest severity score among A, B, C, so B is likely to be a hotspot. Or if there is a service P which does not have a caller or callee that is detected as a hotspot, the service P is likely to be a bottleneck. So applying these observation and filtering, we filter some hotspots, and that is what is called copper grouping. So you can see in this image on the left, you see services before applying this technique, and on the right, you'll see the services after applying this technique. We applied one more filter called slope change filter. So what we do in slope change filter is we basically take a look at the slope of the graph before the hotspot window and during the hotspot window. So if there is a lot of change during the hotspot and before the hotspot, we filter these hotspots out. If there is a lot of change during the hotspot window and before, we basically select them. Later, we came up with generalized severity score. So if you remember LSS, that is a severity score based on latency. What we do in GSS is we see how severe is the latency, and we also see how severe is the error count. And combining these both, we come up with a severity score. Now, we had this lot of approaches. We have this multiple scoring techniques, filtering techniques, and what we observed is a lot of these are good at detecting a certain kind of hotspots. So what we needed was to have an approach which uses all the scoring and filtering techniques that we have. And from that thinking, we came up with something called Hotspot Rank. And Hotspot Rank is basically a previous classifier. And what it does, it uses this previous score, LSS, GSS, slope change filters, and use all of these and come up with a new sort of ranking mechanism. So if you look at the results in the first column, you see the various approaches. The last one is being Hotspot Rank. And on the other columns, you see top 1, 5, 10, 20. So what this means is let's take a look at the Hotspot Rank top 20. So what this means is out of top 20 results produced by this Hotspot Rank algorithm, 90% of the actual hotspots will be covered by the results of this ranking output. So we are taking a look at the recall of this, basically the ranking technique. Since we want to detect all the actual hotspots and we don't want to be more precise, that is why we are looking at a recall metric and not the precision metric. And if you want to read more about the calculation and the approach, there is this blog link which will tell us more about this detection process that we run. And as a result of running this tool, this hotspot detection, what we ended up with decreased load test failure. So the success of the load test percentage increased dramatically. And as a result of that, we have improved memory experience. So our data centers are always ready for the next peak, and they can sustain any disaster that has happened in the other data centers. So with that, I hope you were able to see how you could use data-driven approaches into the operations problem, how you can leverage cross-org partnerships. In this case, we partnered with the data science org, and with the partnership, we were able to come up with this approach. And hopefully you were able to see the kind of techniques that we use to detect these hotspots, and maybe you can come up with something inspired from this. So that is it. I hope this was helpful, and thank you for your time.